Hi, my name is Aseem Jain. I worked at the Sheikh Zayed Institute at Children's National Medical Center under Dr. Kevin Cleary. And my project this year was the symmetric foot modeling system, but I also worked on other things that I will talk about. Alright, so the symmetric foot modeling system is a type of leg prosthetic. Aside from this project, I worked on a surgical R-Notes robot, and I'll go into these various aspects of the project as we go along. So, one of the most important things is the ability to walk. I mean, everyone does it and it's necessary. However, many people often need to get amputated because of usually peripheral vascular diseases. Now, diabetes is also a very common type, and it's because diabetics usually have a loss of nerve endings in their lower legs or areas closer that are not that close to the heart. So, these are like the two main causes of leg amputations. Now, there are really two types of leg amputations. There's below knee amputations that are called transtibular amputations and above knee amputations. Of the two, below knee amputations are generally more common. I think it's something like 47% of all people of all amputees are below knee, and I think 23 for above knee. So current prosthetics, the goal is to try and re-simulate human gait and so that the amputees don't have to spend as much energy walking. Now, passive, there's this huge debate between passive and active prosthetics. Passive prosthetics are usually spring-loaded, so they don't really have any motors in them. And as this study points out, Gates, Aldridge, and Wilkins, that passive prosthetics, usually when you're doing faster, like walking movements or even running or trying to do other types of normal activities, it has gait deficiencies, which leads to the prosthetic user to spend more energy in trying to move. However, active, since they do have motor/servo control, what it does is it reduces that energy that they need to spend so that it simulates the human ankle better. However, even in active prosthetics, there's a couple of problems. First, since there's a lot of sensors and and it's not that simple of a design, it's heavy and it doesn't feel like a human foot. The second thing is the cost. These devices can range anywhere from $5,000 to $50,000. So, the goal of this study was to create an ankle robot, or leg prosthetic, that is targeted for single amputees who have below knee amputations. I want this prosthetic to be both versatile so that it could adapt to different surfaces and at the same time feel like a human foot, and I want it to be cost effective. Alright, so I'm going to I'm going to do a basic overview of how my proposed symmetric foot modeling system works. So the principle behind the system is really that in either case, the left foot mimics the motion of a right foot and the right foot mimics the motion of a left foot. So in a single amputee, the prosthetic wearer, or I guess in this case, actually the single amputee has a right amputated leg and a left strong foot, or the strong foot is usually called the one that doesn't have the prosthetic on it. So the prosthetic is shown in red, and this is like a proposed prosthetic. It's not actually how the design will look like, but it shows a proof of concept. So what happens in this scenario is when the left foot takes a step, a foot sensor will record the data on how much force it applied to the ground. Now, since the left foot is supposed to mimic the right foot and the right foot is supposed to mimic the left foot, it should seem only natural that the right foot or the prosthetic, or if the right foot had been there, it would mimic the force output that the left foot did. So what the goal was this force sensor was going to send data to the leg prosthetic. Then the leg prosthetic would then translate this data into a force output, and when it gets pushed, when it actually makes contact with the ground, it would apply the same foot as the same torque or same force on the ground as the left leg did, and then it would continue on walking. So that's like a basic overview of how this proposed system works. So in order to create this, I needed a couple of things. I needed to first find a force sensor. For the purposes of this study, in order to create it, I'd probably create like a prototype. So the force sensor was probably some really cheap one that I could find off the internet. The wireless sensor system, so this system would be needed to communicate between the left and the right leg. And then all the other parts would either need to be 3D printed or ordered from online. So I was at Children's, we had the luxury of using a 3D printer, and this is what the 3D printed part that I printed out looks like. And this is just like a plastic polymer. So when I wanted to design this leg prosthetic, I wanted to look and, more importantly, be the same weight as a human foot.
So as you can see, this is just the base of the prosthetic, and it looks kind of like a human foot. But more importantly, when I weighed it, it turned out to be around 6 pounds, which is generally the weight of a human foot. All right, so there's other things that went into like this whole trans process. So once the foot sensor receives the data, it's going to send it to this XB wireless communication protocol, and then the XB is going to use a microcontroller called an Arduino, and that in turn is going to control the motor. Now, I'm not going to walk through the entire math, but what I calculated is that if from the force data we can translate into a torque, and then from the torque using this formula right here, we can translate it into like a period of motion that is required for the like prosthetic, and then that can be programmed into an Arduino C++/Java language that is readily available. Now this graph here on the right, it shows like it shows like the ratio between the amount of force applied and the resistance gained in the force sensor. So the force sensor doesn't actually measure force; it measures resistance, and the more force you apply, the more resistive it gets. So this graph will basically give you like kind of like a marking to make your torque calculations afterwards. So before I actually went on building it, because building prosthetics takes years, I wanted to do a stress analysis and a rotational analysis to see if my concept would work. Now, during the stress analysis, I assigned like a plasticky material to simulate what my 3D printer already does, and I applied a weight of about 100 pounds on each one of these locations shown by these arrows. So what ended up happening is that it didn't actually survive the stress test. There was actually a displacement of 1.134 inches on the tip, and that just means that when 100 pounds of force is applied, it's probably the plastic's probably going to bend or break in this case. So for future experiments, I know that now I will need to use a more metal-based solution, which is probably what I had to use even if it weren't a prototype in the first place. So the other results that I gathered were a rotational analysis, and this was the movement around the joint. So what I really wanted to see was here is that if it could generate enough torque in a small amount of time. So generally, the required torque or the amount of force applied is meant by around like is a max of like 1,000 meters per second squares, and that's like if it's like a really tiny foot. So this gets that in like less than 0.1 seconds when you apply a force of about 2 pounds on it. So this test actually worked, and it showed that this type of design is very viable and possible. So some important things that I took away from this was that this type of idea has never really been exposed before, and one of the things that when I talked this over with other orthopedists and other prosthetists, they said that not only could this be used for below knee amputations, it could be used for above knee amputations. In above knee amputations, you already have a robot that simulates the knee movement, except they really have no way of simulating the below the ankle portion of the prosthetic, and they feel that this idea might work there. But another possible advantage could be the fact that it could work on multiple surfaces and in different types of motion. So when you're climbing up a stair, you often climb with your strong foot first, and then your left foot or your weak amputated foot will, since it follows the exact same force data, could then simulate the amount of force needed for the next step. So that might work. Also, another idea not explored is walking backwards. For some reason, I haven't found any literature on like prosthetics being able to do backward motion. And in this case, the principle would be the exact same thing. When the strong foot takes a step back, it would record the data, and it could send it, except it would have to tell it to turn the motor another way instead of the way that it used to walk forwards. But while this does work really well for single amputees, or could work really well for single amputees, it would be a little bit harder for double amputees because you need some point of reference or some strong foot to reference how much force needs to be applied to the prosthetic. So in the future, I hope to actually build this prototype. I'm currently in the process of trying to get all the parts organized and assembling different components of it. So that is all the time. So this is all the time that I have right now. I will put another video with this talking about my surgical R notes project, and you can watch it if you want, just for fun.